interested in the PhD, and I remember at the time I was already taking a bunch of students, so there was not really a place for him yet, but he was very persistent and ended up joining, coming for a project as a TU Delft student, so doing a master's thesis at TU Delft under my advising, and he did a really excellent job. So yeah, I have to keep him for a few years longer, and which worked out wonderfully because he did really nice work, connected very closely with people at NASA, part of a couple of different projects. And actually the current project he's working on, will continue to work on. It's a very exciting project where he's having a major role. Ali is a very independent researcher, the way advisors like it, very hands-off. But I think one of the special things he has is really digs into the explanation of something you've seen. So often students dig a bit and then move on to the next thing. But Ali was always very good at digging deep into the fundamental explanation for anything. And I think you'll see that in his presentation. He's very thorough. To the point sometimes I had to kind of, okay, next topic. But that's a very good trait and really indication of a very high potential researcher. Yeah, on the personal side, integrated really well with the group and helped a lot of students. And yeah, those of you who he helped know who you are. And also very active with the maintenance of the codes and overall group service. So yeah, without further ado, I'll let you present your defense.
Right. Thanks, Keith. All right. Thanks everyone for being here today. So engineers have a bit of a reputation for their love of three-letter acronyms. And I guess I'm living up to that reputation by putting one in the title of my dissertation. So I thought I'd start today by explaining exactly what MDO is. So the O in MDO is for optimization, and optimization is a certain kind of mathematical problem where we have some function f that we refer to as our objective, and our aim in an optimization problem is to find the inputs x for this function that minimize its output. And then in constrained optimization, we complicate matters by adding these new functions. We have the inequality constraints g, whose outputs we need to be below a certain threshold, and then equality constraints h, whose outputs we need to be equal to a certain value. And so we can take numerical algorithms designed for solving optimization problems and use them to help us with engineering design, and that's called design optimization. So here's an example. This is a wing box, which is like the primary structure inside an aircraft wing. And if I know all the thicknesses of the panels in this wing box, then I can use some computational tools to simulate how that wing box responds to some set of forces and compute things that I'm interested in, like how much does this structure weigh and what are the stresses inside it. And then for design optimization, I can pass that optimization problem off to an optimizer and say, vary the thicknesses of this wing box to minimize its mass while maintaining some sort of safety factor that I need under these given loads. And so MDO is kind of what you get when you start thinking about, well, where do these forces acting on the structure come from? And for an aircraft wing, the answer to that is they come from the air flowing around the wing, generating the lift to keep the thing in the air. So now, if I want to simulate the structure, I first have to simulate the aerodynamics of the flow around the wing to figure out what the forces are. But actually, the flow around the wing depends on the shape of the wing, and that depends not only on the wing shape that I designed, but also how the wing deforms in flight. So now actually I have to simulate the aerodynamic and structural behavior of this wing together in a tightly coupled manner. in order to get a physically consistent results. And then MDO says, well, if I have to simulate aerodynamics and structures together, why don't I optimize them together at the same time? So now I say to the optimizer, okay, you can vary the thicknesses of the wing structure and also the shape of the wing. And now that I know both the mass of my wing box and the drag that the wing produces, I can compute something for the objectives that I'm more interested in, like, say, the fuel burn of this wing over some mission. So whenever we solve this kind of aerostructural optimization problem, we're always sort of asking the optimizer to trade off aerodynamic and structural performance. And a really good example of this is choosing the aspect ratio of the wing. So all else being equal, if I choose a higher wing aspect ratio, that wing's going to have lower drag, so better aerodynamic performance, but it's going to be heavier because the aerodynamic forces have a bigger moment arm and induce higher stresses in the wing box. And so the challenge with MDO actually is that for the optimizer to find the correct trade-off between these two effects, it's actually not sufficient to use just kind of simple computational tools that kind of roughly capture the trends of drag and structural mass. We actually need to use really accurate computational models to find that trade-off correctly. And so over the last decade or two, people in the lab that I'm in, the MDO lab, have done a lot of work to enable aerostructural optimization with models of as high a fidelity as possible. So here's an example of optimizing this aircraft wing using about 1,000 design variables describing the structural sizing and shaping, and using RAND CFD coupled to shell finite element models. And so, okay, so that's MDO for aerostructural optimization. And in particular, my dissertation is kind of motivated by this trend that you see here, which is that over the past 50 years, the aspect ratio and consequently the flexibility of commercial aircraft wings has steadily grown. And this has been enabled by two things. First of all, it's been enabled by new technologies that we integrate into these aircraft, like composite materials. But it's also, to a large extent, been enabled by increased use of MDO and just increased use of computing power that allows us earlier in the design cycle to account for these coupled aerodynamic and structural effects. And this has kind of allowed us to transition from viewing this coupling of aerodynamics and structures as kind of a nuisance to actually viewing it as something we can exploit for better performance. The problem is that we might be reaching the point now where these wings flex so much that the traditional structural models we rely on are no longer valid. So these traditional, what are known as linear structural models, they rely on the assumption that the displacements in our wing are small relative to the overall size of the structure. So here, right at the bottom of the slide, I'm showing a cantilever beam subject to a tip force. And you see at this low load level, this linear model predicts the deflected shape fairly reasonably. But as I scale up the magnitude of that force, really all the linear model does is extrapolate this small displacement out further and further, and we get this clearly unrealistic prediction of the deflection. So what I need to do instead is use what's called a geometrically nonlinear structural model. And you see if I simulate the same case with this, we kind of see the behavior we'd expect, where the beam kind of maintains its length and bends inward as it bends up. So as I showed a couple of slides ago, the current state of the art in high fidelity aerostructural optimization uses RAND CFD coupled to linear shell finite element models. There's a couple published examples from people in from aircraft manufacturers doing using RAND CFD coupled to high fidelity nonlinear structural models, but only for analysis, not for optimization. And In terms of examples of aeroelastic or aerostructural optimization done with geometrically nonlinear models, so far those have only been done with lower fidelity models, typically say a beam representation of the structure and like an inviscid panel model for the aerodynamics. So the aim of my dissertation is, first of all, to develop and demonstrate for the first time tools that can do high fidelity aerostructural optimization considering geometrically nonlinear effects. And then secondly, to actually use those tools and try and figure out when and how we need to worry about geometrically nonlinear effects in wing design. So in the rest of the presentation today, I'm first going to talk about developing some benchmark problems for aerostructural optimization. And then I'm going to talk about optimization considering geometric nonlinearity in static aeroelasticity, and then finally in dynamic aeroelasticity. All right. So open and accessible benchmark problems are a really important tool to help us improve the quality of our computational methods. And one of the best examples of this is the AIAA drag prediction workshop, which has been going on for, I think, about 2 decades at this point. And this is really all based around different people in academia and industry just seeing how well their CFD codes can predict the drag on this same common research model. And so the drag prediction workshop and the CRM were so successful that they created a high lift version of the CRM. And that in the last couple of years, I think, has been very successful in testing the capability of different CFD methods in predicting CLmax, which is a very tough challenge. And then on the optimization side of things, there's no sort of ongoing workshops, but there is this set of aerodynamic shape optimization test cases that have seen pretty good take up in the community. And so we wanted to come up with a similar benchmark model and problems for aerostructural optimization. And the first place I thought of looking for a model to use is some of the models they use in the aeroelastic prediction workshop, which is about benchmarking aeroelastic analysis tools. The problem here is that these models they're small wind tunnel models, and their internal structures don't really look like real aircraft structures. And so if I'm trying to use this model to benchmark an optimization tool to see how well it can optimize a real aircraft structure, these are probably not a very good choice. Something that might be better is the UCRM. This is essentially an aeroelastic version of the CRM from the drag prediction workshop. This was developed and released by our lab a couple of years ago, but it seemed, to be honest, a fairly limited uptake so far. And I think this is because it's a pretty big and complicated model, so it's hard for people to get started with it. So I wanted to come up with a more accessible benchmark for people to work on. So I wanted it to be a simple wing-only geometry, but something that still requires high-fidelity tools. And then I wanted to pose a series of sort of increasing complexity benchmark problems so that we could ease into the problem. And so the model that I proposed is called the simple transonic wing. It has a very simple trapezoidal planform that's based on the Boeing 717, and inside has a pretty conventional, simple, conformal wing box. And then along with that model, I posed 3 benchmark optimization problems to solve using the model. So in the first one, we're just optimizing the structural sizing of this wing subject to structural failure constraints in these 2 maneuver conditions. In case 2, I add a cruise flight condition, and based on the lift and drag in that flight condition, we can compute a fuel burn over some nominal mission, and that becomes the objective to minimize. And then we also give the optimizer control over the twist distribution and section shapes of the wing. And then finally, in case 3, we also give the optimizer control over the planform geometry of the wing. So back at SciTech 2024, I proposed this model in a paper, and I also published online all of the files that I thought people would need to tackle these problems. And since then, the benchmark got picked up by this AIAA working group, and at SciTech 25 in January this year, we had myself and groups from 4 other institutions present our results of applying our tools to these benchmark problems. And this year, we're continuing to develop the problems, and we'll have more new results at SciTech 2026. So just to motivate the next part of the dissertation here, I'm showing my results for the 3 benchmark problems here. And you can see that the case 3 design here at the back is really deflecting a lot in this maneuver condition. And this kind of level of displacement is far beyond what people traditionally think linear structural models are good for. So we need to be able to do aerostructural optimization considering geometrically nonlinear effects in these static maneuver conditions. So the first thing we need for that is the ability to do geometrically nonlinear structural analysis. And so within the finite element library that I use in this work, TAX, I implemented a nonlinear solver. And this solver combines Newton's method, which is a very well-known method for solving nonlinear systems of equations, combines Newton's method with a load adaptation, load incrementation scheme, where instead of just applying the external loads fully in one go, what I do is I scale the external loads down, solve for the displacements under those scaled down loads, and then repeat the process, gradually increasing the loads till I get to the full magnitude. And I have a process in there for adapting the size of those load steps based on how hard it was to solve the last increment. And something I added to this solver to improve its efficiency is what I call equilibrium path extrapolation. So you can imagine as I go through and solve each one of these increments, basically what I'm doing is I'm finding a point on the equilibrium path of the structure. And then typically what I do is once I've solved for the displacement at this load factor here, I increment the load and I start solving for the displacement at the next load factor, and I just start from that last point that I found on the equilibrium path. But actually what I implemented is that I save the last, say, 3, 4, 5 points on the load path. I essentially do a polynomial fit and use that to extrapolate forward to the next load factor, and this gives the Newton solver a much better initial guess, which makes it hopefully converge faster. Another thing I implemented, which there's more details on in the dissertation, is adaptively controlling how tightly I converge the linear system that has to be solved inside each Newton iteration, which is most of the cost of these nonlinear solutions. And so by relaxing how tightly I need to solve those equations, and also relaxing how often I update the preconditioner, which is a very expensive operation, you can see in this case that I get just over 2x speed up. Okay, so now we have the ability to do geometrically nonlinear structural analysis, but to do fully coupled aerostructural analysis and optimization, we need a couple more things. First of all, we need an aerodynamic model that correctly computes the magnitude and orientation of the aerodynamic forces based on the deformed configuration of the wing. And here we kind of automatically get this because I'm running CFD directly on the deformed shape of the wing. But another thing we need that I see mentioned or talked about a lot less is that the scheme that we use for transferring loads and displacements between the aerodynamic and structural meshes also needs to be valid for large rotations and needs to compute the load transfer, again, based on the deformed configuration of the two meshes. And here I'm using a scheme called MELD, developed by Graham Kennedy in his lab at Georgia Tech that does both those things. All right, so now we can finally do some optimization. And I'm going to go back to those benchmark problems and solve the third most complex one of those benchmark problems. So as a reminder, in this case, we have 3 flight points that we do analysis at, cruise condition that we use to compute a fuel burn, and then 2 different maneuver conditions where the structure has to have a safety factor of 1.5. And to investigate the impact of geometric nonlinearity, I'm going to solve this problem twice. Once with the linear structural model and once with the nonlinear structural model. For designing the structure, we have a little over 300 design variables. And what that corresponds to is for each one of these differently colored panels on the wing box here, I have design variables controlling the thickness of the skin, and then 2 variables for the geometry of the stiffeners. And then controlling the geometry of the wing, you see here I have design variables for the twist at each section of the wing, the chord length of the root and tip, the span of the wing, the sweep, and then finally moving these points up and down, I can control the cross-section shapes of the wing. All right, so here's the 2 optimized results with using the linear model on the left and the nonlinear model on the right. And if you're having trouble telling them apart, that's not your fault. That's because they are incredibly similar. So in terms of the planform, the nonlinear wing has a slightly higher span and aspect ratio, 1 to 1.5%. But in terms of the overall performance that we're optimizing, the fuel burn, the difference in performance here is only 0.2%. But what you should keep in mind here is here I'm comparing to the fuel burn predicted by for the linear design, predicted by the linear model, which I've been telling you up to this point is not a valid model for wings that deflect this much. So what I did after the optimization is take that wing design that was optimized using the linear model and reanalyze it using the nonlinear model. And you can see when we do that, the sort of effective span of the wing in flight is reduced as we would expect. But actually the impact of this on the fuel burn of the wing is not that big. And somehow, actually, this wing that I designed, I optimized using the linear structural model. When I reanalyze it, actually has a better fuel burn using the nonlinear model than the wing that I designed with the nonlinear model, which seems surprising. And the reason for this actually is that this wing, the linear design, is structurally infeasible. Right. So here again, I'm comparing, in this case, the structural failure criteria, again on the linear design, analyzed with the linear and nonlinear models. And you can see that in the wing ribs, but also the skins and spars, this linear design no longer has that factor of safety of 1.5 that we need from it. And the reason for this is something called the Brazier effect. I'm not exactly sure. But so you can imagine any engineer who's taken a structural mechanics class will tell you, if I take a beam like this wing and I put it under some bending moment, then I get compressive stresses in the upper skin and tensile stresses in the lower skin. And this rib that connects the upper and lower skins, in this case, it's just kind of sitting here totally unaffected by these loads. But if I actually consider now the deformed geometry of the wing, now these compressive and tensile stresses gain vertical components, and they put this rib under a crushing load, which can cause it to buckle. And actually, in the dissertation, I go into more detail about how actually this same brassiere effect also leads to the increased stresses in the wing skins and the wing spars. Okay, but so at this point, what someone who actually designs real aircraft might say is that, well, this is not so much of a problem because, you know, at this point I'm optimizing the structure at a relatively low level of detail, and at some point later in the real design process, I would go back and resize the structure in more detail, and then that structure would be safe and would be fine. So then the question is, well, okay, if I go back and resize that structure later, how much is that going to change the structural mass of the wing? And was it then a bad idea for me to choose the plan form of the wing in that initial optimization based on the linear structural model? And so what I did to investigate that is, again, using the nonlinear structural model, I took the design that was optimized with the linear structural model, and I re-optimized it, but only re-optimizing the structural sizing. So the shape of the wing was fixed at the design optimized using the linear model. And when we do that, yes, the fuel burn is finally now worse than the wing that I designed with the nonlinear model from the start. But the difference in fuel burn here is, to be frank, pretty insignificant. It's 6 kilos out of 10 tons. So I think we can conclude that for this wing, for this optimization problem, geometric nonlinearity really does not have a significant effect on the design. But I don't want to draw huge sweeping conclusions just from one wing and one design problem. So I ran a couple of other optimization studies to see if geometric nonlinearity mattered more in a few other situations. So for wings that fly at transonic speeds, if they fly too fast or at too high an angle of attack, you get something called buffet, which is where this shock wave forms on the wing. You get separation behind that shock wave, and that oscillates backwards and forwards and leads to a lot of vibration in the structure. And this has to be avoided throughout the flight envelope. And so my theory here is that we kind of intuitively know that higher Mach number flows are more sensitive to small changes in the wing geometry. So maybe if I optimize this wing, considering some of those higher Mach number flight points, geometric nonlinearity might have more of an effect on the design. So I went back and solved basically the same optimization problem as before, but now with two new flight conditions, one which I call a high lift buffet condition and one a high speed buffet condition. And in both of these flight points, I add a constraint that there has to be below a certain amount of flow separation for the wing to be buffet free. And you can see in this video, if you look at the wing on the left there, that the optimizer is able to shape the wing to get rid of that separated flow in this buffet condition. And again, it does greatly increase the aspect ratio of the wing, a little less than those results that I showed before. But again, if we look at the planforms and sort of overall performance of these two designs, they're pretty much as similar as they were before. So like a 1% difference in the wingspan and a 0.3% difference in the fuel burn. But something that changed perhaps a little bit more is the buffet behavior themselves. So in this high lift buffet condition, the constraint on the wing really is that it needs to have a 0.3 G margin to buffet. And that means it needs to be able to get up to the point where it's producing 130% of its weight in lift without buffet onset. And you see with the yellow and blue lines, the two optimized designs, when you analyze them with the model they were optimized with, they achieve this. But when I take the linear design, reanalyze it with the nonlinear model, I lose about just over 10% of that profit margin, which, to be honest, I'm not entirely sure how significant effect this would be in reality, but I think you could argue that that's more significant than the differences we saw before. All right, and the final study I did in this section is seeing if geometric nonlinearity matters more for unswept wings. And this is because backward swept wings have this property, this natural tendency that when they bend upwards, the tip of the wing twists down. This shifts the aerodynamic loads inboard, which is good for the structure. This is a beneficial effect. But for wings that bend a lot, this effect caused by the wing sweep kind of dominates all other effects that change the lift distribution of the wing. And so I wondered if we optimize an unswept wing that doesn't have this dominating effect, maybe geometric nonlinearity will have more of an impact on the lift distribution of the wing and therefore the structural sizing. And so I ran, again, basically the same optimization problem, but adapted to this unswept wing model, which is described in more detail in the dissertation. And at the overall level, the answer is basically no. It doesn't make much more difference. Again, around a 1% difference in aspect ratio and a 0.2% difference in fuel burn. Although in this case, actually, the nonlinear optimized design has a slightly smaller aspect ratio. Okay, one interesting physical effect that showed up here is that when I look at the how the wing twists in flight in that 2.5 G maneuver condition, when I use nonlinear analysis, this wing actually twists in the opposite direction in flight than when I use the linear model. And this is due to something that I refer to as the drag torsion coupling. And I'm not the first person to talk about this, but essentially, drag forces typically don't have much of an effect on the wing, or we don't think of them as doing, because they try to essentially bend the wing in this like chordwise back and forth direction, and that doesn't really affect the aerodynamics much. But if you consider a wing that's bent upwards quite a lot already, now that drag force at the tip actually can induce significant torsion in the wing and change its twist distribution in flight, which does affect the aerodynamic loads quite a bit. But in this case, actually, the direction that I'm seeing the wing twist in the nonlinear case is actually the opposite direction that I would expect from this drag effect. And that's because at high enough angles of attack, the lift force actually gains sort of a forward component in the wing's reference frame, and that actually causes it to twist in the other direction from a drag force. All right, so now we can move on to considering geometrically nonlinear dynamic aeroelasticity in these optimizations. And specifically, I'm going to be talking about flutter. And flutter is basically the onset of unstable oscillations that occur due to the interaction of the natural vibration modes of a structure with unsteady aerodynamics. And unlike a typical vibration mode of a structure that would just kind of die out over time, when we get flutter onset, these aeroelastic modes will just grow exponentially and can eventually cause catastrophic failure. So again, we have to avoid this throughout the flight envelope. And so constraining flutter in aerostructural MDO is a pretty active research area. Here on the left, I'm showing an example from one of my lab mates, Erica Johnson, who did this using a traditional DLM panel aerodynamics model. And on the right, I'm showing some results from the team at NASA Langley, who are doing very high fidelity flutter prediction with linearized frequency domain, CFD. The problem with these two methods is that they're what I call geometrically linear methods, which mean they're computing the flutter stability of the wing based on its undeformed configuration. But really, for a wing that flexes this much, we actually need to consider how the in-flight deformations of the wing affect its natural vibration modes and how that affects flutter stability. And I refer to that kind of analysis as geometrically nonlinear flutter analysis. And so geometrically nonlinear flutter constraints have actually been included before in aerostructural MDO, but again, only with lower fidelity models. And actually, these models at this fidelity are actually often sufficient for flutter prediction. But as I mentioned in the introduction, they can't necessarily do this accurate trade-off of drag and structural mass. And so we can't do aerostructural optimization with these models on their own. And so in this section, what I'm going to do is sort of keep the same sort of workflow that I was using before, where we have our detailed structural model, couple it to RAND CFD to analyze steady state flight conditions and compute things that we care about, like maneuver stresses, mass, lift and drag. But then at the same time, I'm going to condense that detailed wing box model down to a beam representation. I'm going to pass that beam to UMNAST, which is a nonlinear aeroelastic simulation toolbox developed by Professor Sesnick here at the University of Michigan. And then UMNAST is going to do some geometrically nonlinear flutter analysis that I can compute a flutter constraint in my optimization problem. And so in the dissertation, I go through all the details of how this process works. But mainly what my work was focused on is adding a geometric parameterization to this framework so that we can optimize the wing shape and structure at the same time. And for that, I'm using something called the freeform deformation approach. This is the same approach that I showed in the last section. And the reason for using that here is first, that it's fast and it's easy to compute derivatives through, but actually most importantly for this work is that the FFD method can very easily parameterize the geometry of multiple different models of a wing consistently. And that's really important in this case, so that as I change the geometry of the wing, the geometry of both the detailed model of the wing and the beam model remain consistent with each other, which is what I'm showing here. All right, so all the results that I'm going to present here are on this pretty simple wing model. It's just an unswept, untapered NACA 0012 wing. And I place these concentrated masses along the trailing edge of the wing to make it flutter inside a reasonable range of flight speeds. And all the flutter analysis results that I'm going to show are computed over a simple sweep in flight velocity at sea level. What we do is for different cases, we change the angle of attack that we do that speed sweep at, and that leads to different levels of in-flight deformation that we're computing the flutter stability around. And so before I did any optimization, I actually did a fairly extensive set of analysis studies comparing the predicted flutter stability of this wing when I use a linear or nonlinear beam formulation in UMNAST. And what we found is that when I use a linear beam, not only do I mispredict the flight speed at which flutter occurs, but I can also mispredict the critical mode, which actually can have serious consequences if I'm then optimizing the structure of my wing based on these predictions. All right, so now we can do some flutter constrained optimization. This is a similar but simpler problem to the one I was solving in the last section. So I'm optimizing just the thicknesses of these panels in the wing box, and then the span and sweep of this wing to maximize its cruise range. And then I have constraints again on stresses in a maneuver condition, and then on flutter stability over this range of flight speeds. And so I ran a bunch of optimizations. First of all, varying this angle of attack that we compute the flutter constraint at to see the effect of computing the flutter constraint at different levels of deformation. And then also I repeated all of those optimizations with either the span or the sweep of the wing fixed to gain some insight on how the planform design of the wing is affected by this flutter constraint. And so again, in the dissertation, there's loads more results than this, but I think this plot kind of summarizes most of the important things. So the first thing to notice is on the far left of this plot, this is when we're computing the flutter constraint at the lowest level of in-flight deformation. And at this point, what you can see is actually that including the flutter constraint versus optimizing, just not considering flutter whatsoever, it doesn't make any difference. These wings achieve the same cruise range, whether or not you have the flutter constraint. But then as I increase the angle of attack, as I increase the deformation level of the wing that I'm computing the flutter constraint around, the achievable cruise range of these optimum designs steadily decreases. And in the dissertation, I talk about why exactly this case where I fix the wing span, the cruise range is affected a lot more. But I think the most important thing to notice here is actually that we see quite significant loss in achievable cruise range, even when the flutter analysis, is performed with wingtip deformations of even 5 to 10% of the wingspan, which is where we would typically think linear structural models are perfectly accurate. And it's not just the cruise range of the wings that are affected, but also the design themselves. So here I'm showing for the wingspan, we get between a 5 and 10% reduction in the optimal wingspan, depending on the level of deflection that the flutter constraint is enforced at. All right, so to wrap up, I thought I'd try and distill some takeaways for you, where I guess you really means people who design actual real aircraft. I guess the first and perhaps most surprising takeaway is that I found, even for very high aspect ratio wings with deflection levels up to 30-35% of their semi-span, in the sort of flight conditions that I was considering, cruise and sort of static maneuvers, actually geometric nonlinearity didn't really have much of an effect on the static aerodynamic performance of these wings. So their lift, their drag, and the sort of global aerodynamic loads. I did, of course, see that the internal loads in the structure, and therefore the sort of structural factor of safety, was more significantly affected. But what I found is that when you size the structure with those loads, didn't really affect the overall mass of the structure that much, and so these internal nonlinear effects in the wing box, they don't really affect the overall trade-off of aerodynamic and structural performance. But then in the last section, what I just showed is that actually, even for deformation levels where a linear model perfectly accurately predicts the in-flight deformed shape of the wing, it actually can't sufficiently accurately predict what I would describe as quantities that depend on the behavior of the wing about its deflected shape. And so the example I showed here was on the flutter stability, but I think this similar sort of magnitude of effect would extend to things like flight dynamics, static stability, and maybe even control effectiveness. All right, so in terms of novel contributions in this dissertation, I think there are probably 4 or 3, depending on how you count them. First of all, I created this simple transonic wing benchmark, and that has allowed researchers from across the world to compare their tools on the same aerostructural optimization problem really for the first time, I think. And then I developed some new methods. First of all, for aerostructural optimization, where we include geometric nonlinearity in the detailed structural model. And then when we include geometrically nonlinearity in this flutter constraint. And then finally, I didn't just develop these tools. I also, went out of my way to try and figure out if and when we should actually care about geometric nonlinearity. For the committee, here's the papers that I've written or helped write during this PhD, some of which are related to this work, some of which aren't. Yeah, and so finally, I have a lot of people to thank for getting me to this point. So first, I want to thank the committee, to Matthew, Carlos, Graham online, and Keen for your help with graduating. And next, I want to thank a couple of collaborators that I've had the good fortune to work with over this PhD. So first of all, this flutter constraint work that I presented at the end was actually the first thing I did in my PhD, part of this project with Airbus. And I was really, really lucky in that case to be put on this project with two postdocs, Erica Johnson and Christina Riso. And I really couldn't have asked for better collaborators, for a better, start to my PhD to be paired up with them. Another collaborator I have is Eitan, my MDO lab mate, with whom I wrote this paper about airfoil shape optimization that is completely unrelated to my PhD research. And somehow that meant I got a free trip to Stockholm to watch Eitan present our work. I didn't have to do anything. And then
You're welcome.
And then back in November, I actually went to visit Graham Kennedy's group, Georgia Tech, who were kind enough to host me for a month. And then there's actually several people at NASA whose work my research really relies on. The teams behind the development of MFIS and OpenMDO, so people like Brett Stanford, Kevin Jacobson, Andrew Thalen. And I want to give a particular shout out to Tim Brooks at NASA Glenn, whose development work on tax, really my entire PhD almost would have been impossible without. Yeah, then I want to thank first of all King for having me in your lab. Yeah, this picture on the top left is from the 2019 MDO Lab workshop, which I think was literally like 2 weeks after I joined the lab. It's interesting that actually I'm the only person, oh, maybe Erica as well. We're the only two people still in the lab from that photo, actually. And I think I've been really lucky that the people in the MDO lab are not only my lab mates, but also some of my closest friends. And I don't want to give specific shout outs, but I will thank the fellow members of the three nut trio, my office mates, Hannah and Eitan. Yeah, and then other friends in the air department as well. My housemates over the years, Gabby, Alan, Cantaloupe, the cat, Bree, and Alana. And finally, I want to thank Fariel for being really my biggest supporter over these last 5 years. And then my family, my parents who are here all the way from Scotland. And finally, I want to thank my granny, who unfortunately passed away in December, but actually for the last year and a half, I've kept this birthday card that she sent me above my desk because in it it says you're getting to be too old to be a student. And so with that, I'll take your questions. Thank you.
All right, open for questions. Patricia.
Can you elaborate on what you did for improving the efficiency of the Newton solver? So the interpolation process that you described, like what would you use, how many points?
Yeah, let me try and find that slide. Yeah, so what I do inside the solver is I save the last n solutions of each load increment, and n is the user can choose the number, but typically like anywhere between like 3 and 6 points. And then I use Lagrange interpolation, which is equivalent to like fitting a polynomial through the points. And then I just evaluate that polynomial at the next load factor that I'm solving for. And that gives me this prediction of the next point on the equilibrium path. Does that answer the question?
Yeah, I would have like I've asked you more, but thank you.
Bila?
In the slides where you were showing the linear model, the nonlinear model, and the reanalyzed linear model, could you speak a bit to, I think I missed the clarity on, you were reanalyzing the linear model using the nonlinear model. That's the statement I remember.
I'm reanalyzing the linear design. So the design that was optimized using the linear structural model, I'm taking that design and reanalyzing it with the nonlinear model.
Model or analysis?
I'm using those two words interchangeably.
Okay,
Yeah.
because like I was confused, how do you analyze a linear model using a nonlinear model?
Yeah.
Okay, so this is on the STW benchmarking that you
Yeah.
created. While I find your insights on the how much the nonlinear or geometrically nonlinear, somewhat what I have also seen in my own work,
Mhm.
I'm curious to know if you can generalize that. Besides on this specific test case, what about, for example, you think on the UCRM or 787 or something different than a test case that you've created? How would you?
Yeah, so I think it might be hard maybe to generalize the differences that I see in the optimized designs, maybe because that's a little more dependent on the exact formulation of the optimization problem. But in terms of the fact that, you know, when I reanalyze this wing, there's very little change in, say, the cruise drag and the distribution of aerodynamic loads. You know, for a wing of this high an aspect ratio, I think that's more generalizable. And also, I mean, the thing to consider here is this wing has an aspect ratio of like 19, which is well above like what we're seeing probably even in the next generation of aircraft wings. So if anything, you know, in real aircraft, this effect is going to be even smaller, likely.
Sorry, just two questions if you have time. So the first question is, if you right now someone asked you to develop an aircraft design framework for conceptual and like early preliminary sizing, like what aerodynamics models would you select and what structural models would you select and what kind of company? The second question would be sort of similarly. Recently, there's just been pretty public with X66 being paused. Like, does anything that you've learned here support that kind of decision, or does it provide any hints for that? I'm just curious. Sorry.
Yeah. So on your first question, how would I, you know, if I was designing a real aircraft, how would I do it? I think I would go to something kind of similar to this this flutter constraint framework that I had, because one of the big problems in all of our optimization problems is that because we use such expensive models, we can only consider like a handful of flight points. But in reality, you have to size a wing structure based on literally on the order of 1 million different load cases. And so what I would probably do is for most of those load cases, I would take an approach similar to this, where you take your detailed model, condense it down to a beam, maybe couple that to something like a panel method, much cheaper than CFD, do the aerodynamic analyses there, and then extract the aerodynamic loads and apply them back to the detailed wing box model for sizing. And actually, while writing the dissertation, I found a paper from some people at Airbus proposing exactly that approach that maybe they use in-house. Yeah, but they're doing that only for structural sizing of the wing, where of course I would still like to include, you know, the aerodynamic shaping of the wing at the same time. Your question on the X66, like whether anything here supports the decision to stop caring about truss brace wings, I guess. I'm not sure exactly. Actually, the truss brace wing, even though it deflects less in flight than we show here because of the truss, some people have actually shown that even at those lower deflection levels, you actually need to use nonlinear analysis to correctly capture the loads in that truss. But I think what they're focusing on now, instead of the truss brace wing, is what they call like a thin wing, which is really just an even higher aspect ratio wing, where yeah, I mean, traditionally maybe you would have thought higher aspect ratio wing, higher deflections, you might need to consider these things, but well, evidently not for static aeroelasticity. It doesn't seem to matter that much, but for dynamic things like flutter, yeah, it definitely matters. And even at much more moderate deflection levels, like we see already in aircraft like the 787 flight.
All right, hey, done. This is the line. Yeah.
Question online?
Yeah.
Yes, there's a hand raised, so I guess he'll.
Oh yeah.
Yeah. Could you go to slide 129?
29.
Very connected.
Yeah.
So here, some of the points for the span plus sweep case looks like they have lower range than just with span. Can you explain that?
I think that might be because the points are offset in X. So because here I'm plotting against the wing tip displacement in the flutter condition, but actually what I varied is the angle of attack that the flutter constraint is computed at. So actually, if you plot, I might have a plot of that actually. Yeah, here we go. So if I plot it instead against that angle of attack, so comparing like for like optimizations, you see the blue line is always below the yellow line.
Gotcha. Thanks.
Any others?
Yeah, just a question. The two cases you were showing, one with the geometrically nonlinear and then one with the linear one between the two simple benchmarks. Did you notice a lot of optimization behavior differences, or presumably per iteration is more expensive? But
Yeah. So the cost, the difference in computational cost was kind of case dependent. It ranged anywhere from like 25% more expensive to like twice as expensive in some cases to do it with nonlinear. But in terms of how challenging the optimization problem was to solve, it didn't seem to make much difference.
did you ever try like restarting one from the other or anything like that?
I think I did a couple of times. Yeah. It worked. Yeah. But it's better to start from one using the same structural model because of those differences in the structural failure criteria. Yeah.
You ever considered what the impact would be if you held your cruise condition with RAN CFD as you are, but then did all your other flight conditions, the lower fidelity aerodynamics model?
Yeah, that's something I've wanted to try, and I haven't gotten around to testing it. But yeah, I mean, you would expect that you could get away for these like subsonic maneuver conditions with just using a VLM, but I haven't tested it yet.
Any other questions? Here or online, nothing else? All right, so thank you all.
May I? This is Antoine online. I don't know how to raise my hand online. So
Yeah, you have a question, Antoine?
yes, please. On slide 83, you were showing the effect of drag on twist.
Mm-hmm.
So can you go back, please, to the slide? I was trying to get a feel of how much of an effect it has on span load. Or 0.2 degrees. So it's not that you're saying it has a more nose up attitude. It twists less.
In this case, when you use the nonlinear model, you get more washout in the maneuver condition. By, I don't know, what is that, about half a degree or more? But yeah, actually in this case, it didn't have a particularly significant effect on the span load because the structural sizing of these two optimized designs ended up being pretty similar.
I find it a bit surprising because 0.5 of a degree is non-insignificant. I mean, it is significant. So what do you mean by that? The structural model recuperated? Because a little more outboard, I would have expected the optimizer to not go as high as an aspect ratio for that. Because it's
Yeah. I mean, I haven't really figured out exactly why. I'm just looking at the end result is that the design optimized with the linear versus the nonlinear model, they have similar aspect ratio and structural mass. And also when I do plot the lift distributions in the maneuver condition, there's a small difference, but as I say, it doesn't seem to affect the eventual structural mass of the wing.
I'm trying to figure out what is it that the optimizer did to compensate that.
Actually, it didn't really seem to do that much. Yeah, the jig twists of these two designs are a little bit different, but it seems like the performance was relatively insensitive to those differences in jig twist that were like of a similar order of magnitude, like half a degree.
Okay, thanks.
Thanks.
Bravo.
Thank you all. So, so I'm gonna stay on this thing or moment.
Yeah, I figured you would.
Yeah, this one.
Yeah. I
Okay,
guess.
so everyone online, please log out. We're gonna start the private grilling session. If we can stop recording at this point.
Oh yeah.